Morning to everybody, and I welcome you once again to be here with me together, and we try to understand some basics of string theory and superstring theory. So, as we were discussing last time, that our superstring theory action or action of the superstring theory in the so-called RNS formalism, Raymond Nebus's formalism that we are doing. This has supersymmetry on the bird seat. Okay, so we introduce the fermionic fields on the bird seat, and like in our bosonic string theory, we have our bosonic fields, massless bosonic fields, denoted by capital X mu, and they are functions of tau and sigma, the bird seat coordinates. Okay, and the fermionic fields are also functions of tau and sigma, the bird seat coordinates. Sigma and tau we could write either as tau and sigma or as sigma plus sigma minus in the right front coordinates. We will. So what I thought that perhaps we could recap the important key points of the bosonic string theory. We have limited time, so we could have a bird's eye view, okay, or an overview of what we know about bosonic string theory. I keep her concerns also in mind. A few things it may be better to recap. So let me briefly touch upon the important key points of the bosonic string theory, which is an integral part of the superstring theory. You add this fermionic part to the bosonic part. So the bosonic part is something that we must consolidate and we must know all the time what it is, and then what are the new additions to our theory, what are the new modifications to our theory. Okay, like whatever you have energy momentum tensor for the bosonic string theory, you will have some T alpha beta or T mu nu. Now the presence of this fermionic part of the action would modify that T alpha beta. There would be some additional terms and so on. So we need to keep a control on these things, and we need to know the key points. So I am not forgetting drinking my chucks and bothering you less. Yes. All right. So let me briefly start with the so-called recap of key points of bosonic string theory. So the very first point is relativistic point particle, and so when we consider the motion of a we can parameterize the motion of a particle in the space-time manifold by some parameter tau. This parameter tau is a parameter that parameterizes the word line. So as the particle moves through the space-time, it sweeps out a trajectory which is called as the bird line. So bird line is the trajectory of the relativistic point particle. Okay, and this can be parameterized by x mu of tau. So x mu of tau, this tau in general is a general parameter, but it could be identified also with the eigentime if we like. Okay, and eigentime is the time that we measure with our own watch, which we carry with us. Okay, if I'm carrying my watch with me, whatever I measure here, this is the proper time for me. Okay, so eigentime or the proper time, and so x mu are the coordinates that help us understand the motion of the relativistic point particle. And so we parameterize things in this manner. And here, the action of the theory is seen to be proportional to the length of the word line that is being swept between the initial and the final point. Okay, so this is minus MC ds between two points, and this could be written as minus MC, and here it could be, let us say, S1 to S2, and here I could write it tau 1 to tau 2, and ds would be minus eta mu nu dx mu, that is my ds, and I can this signature that we take, and this is and this could then be written as if I write x mu dot x mu dot, or if you don't like to introduce these derivatives at this point, then you can call it and this, if we like, we could express this by x mu dot and this by x mu dot. So I could write we could introduce the notation x mu is dx mu over d tau, and x mu dot then would be dx mu over d tau. Then your xn would be minus square root of eta mu x mu dot d tau. Right? This in fact is called as the Nambu-Goto type of action. This is called the Nambu-Goto action. But in general, in field theory, we would call all the actions that involve a square root as the Nambu-Goto type action. So you could put in more fields into the theory. So Nambu-Goto action, Born-Infeld Nambu-Goto action, Dirac-Born-Infeld Nambu-Goto action. Okay, as you keep adding the fields. If you add the electromagnetic field inside the square root, you call it Born-Infeld Nambu-Goto action. If you introduce also two-form gauge field, you call it Dirac-Born-Infeld Nambu-Goto action, and so on. These actions are usually a little bit more difficult to handle. You can handle them, of course, but they involve a square root. So when you take this will always hang around upstairs or downstairs. Okay. And an alternative way, but before we need to understand this. Here mu takes the values 0, 0, 1, 2 into D minus 1 or capital D minus 1 as you like. So, for example, 25. Okay. And if one is talking in terms of, this is called as instant form of dynamics, and you can also describe it in plus minus 2 into, this is called as light front dynamics. Okay. So this x mu is a mu vector in the space-time manifold. However, this x mu is a scalar on the bird line. Okay, because the bird line does not see its index pair. Okay, all right. So the other alternative to describing this, there is one difficulty with this, that if you consider massless particle, then this action is not enough to describe because it's having mass as a coefficient sitting outside. So for a massless particle, it would be 0. So you cannot describe with this action a massless particle, and therefore you think of an alternative which we so